Hello everyone. So today I'm going to talk to you about a field deployment that we carried out at a bridge in Bradford. So we want to test out this new technique for monitoring scour called vibration-based scour monitoring. So throughout this conference, you come across various different ways that are being used to monitor different types of bridge failures. So what do you think is the main cause for bridge failure? So out of large number of causes for bridge failures, scour and flooding is the main cause for bridge failure. When we compare with others, scour and flooding outnumbers all other causes for bridge failures. For those who are not familiar with scour, let me give you a brief introduction. Scour is the removal of material from around a bridge foundation because of the fast flowing nature of water. So especially during flooding, when there is so much eddies created, there can be erosion around the bridge foundations, which can lead to even bridge failures. So the traditional way scour is monitored is by using divers, but this method has so many problems because it's dangerous and also it's not reliable. So the structural vibration-based scour monitoring technique, which I'm going to talk to you about today, is the theoretical background of that method is like this. So when scour occurs around a bridge foundation, because the soil which was supporting the bridge foundation previously is not there anymore, the stiffness of the bridge is less. Because the bridge stiffness is lower, the natural frequency is also lower. So this change of natural frequency can be measured by using simple accelerometers on the bridge. And we can correlate that back to the scour depth by using a finite element model, or we can use the natural frequency itself as a measure of scour-induced damage. So the problem with this method is that lots of researchers have carried out numerical models and found out that scour is in fact, natural frequency is in fact sensitive to scour. But the problem is validating this in real life because we would have to place accelerometers on a bridge and wait for the bridge to scour for a long period of time. So we decided to take a different approach, which is monitor scour in reverse. We found a bridge in Bradford, which is called Baildon Bridge in Shipley. This is a three-span bridge, and it has a history of flooding. As you can see, there's serious flooding. And the first thing we did was we wanted to carry out sonar scan with the bridge cat vehicle, which is owned by Cumbria Council. So this bridge cat vehicle has an extendable arm with a sonar head at the top. And so this sonar head can be put into water, and we can take images. So these are three sonar images overlaid with each other to get the bed profile. As you can see the bed profile before the repair. And then after the repair, you can see in this color, you can see that after the repair, the bed level has gone up. The bed level rise because of the controlled addition of soil was about 1.8 meters. So initially we created a finite element model to simulate this behavior, because before installing the instrumentation, we wanted to understand what sort of mode shapes we are looking at and also what sort of natural frequencies we are looking at. So this is the finite element model that we developed. It was using CSI Bridge commercial finite element software. So the bridge deck was modeled using, slabs were modeled using shell elements, which can be used to give the area elements which have out of plane bending and also in plane bending. And the beams were modeled using frame elements which have beam column formulation. The soil pile interaction was given idealized using Winkler spring model. So the soil stiffnesses were provided using small strain stiffness. So so with scour, our simulation showed that with scour, the natural frequency of the bending mode is 16.37 hertz, it should go up to 17.1 hertz because of the repair program. So because of Scour, we should see the reverse effect. So the installation of instrumentation we used, because this bridge is a short span bridge which is very stiff, we wanted to use high sensitivity accelerometers. We used this accelerometer, each costing around £1,000 each. We used 10 of those accelerometers on the bridge. They have very low noise and high sensitivity. And the data logger system we used is here. So we use a Raspberry Pi to transfer data from the site to a server in Cambridge. And we use National Instruments compact Rio system to log data. So the software requirement was that we wanted to log measurements from 10 sensors simultaneously at 200 hertz, and also we needed a system which can run without any intervention. This is the sensor locations that we used. So we used 7 sensors in one vertical plane along the edge of the bridge, and 3 other sensors along the midsection of the piers. Unfortunately, 2 sensors didn't work, probably because of the sensor cable failures. And this is how we attach the sensor cables and accelerometers. So, and then the modal analysis was carried out using something called Fourier frequency domain decomposition. Compared to other traditional spectral density functions, the advantage of using Fourier domain frequency domain decomposition is because it gives all sense channels can be used to just give one spectral density function. So all the 10 like 8 sense channels which worked gives only one spectral density function, which is called the first singular value. A peak in first singular value indicates a mode shape. There's a peak here as well, but it's not very consistent. So we saw 2 peaks, one at around 4.5 hertz and one at around 18.75 hertz. So the assumptions we made was that we assumed that the traffic excitation during peak hours, which is the time we considered, was wideband, because the FDD works only when the input excitation is wideband, because it's a output only method. There's no input given. And also we assumed that within this period of time, there's no significant change of temperature, water level, and because of that, we should see the same natural frequency. But what we noticed is that these peaks, so from the same day, within 1 hour period, different 10-minute data sets showed that the peaks actually changed quite a bit. So 4.5 hertz peak has about 0.6 hertz error, whereas 18.75 second mode has about 18.8 hertz error. And the mode shapes we found out at each of these different data sets. If you compare these different data sets, so this data set to like different data set, we can see that all of these have a similar mode shape. Mode shape was, so we can use modal assurance criteria to compare 2 mode shapes. Modal assurance criteria gives a number from 0 to 1, 1 being very similar. So we can see that different mode shapes at different times give the same mode, like about modal assurance criteria above 95%, which means that we are actually in fact detecting at 4.5 hertz and 18.75 hertz, we are detecting real modes. And then we went to the mode shapes. The first mode at 4.5 hertz was a sway mode. And as you can see, this is the mode shape we observed using modal analysis. And initial FE model actually did not detect this mode shape. The reason was that because we did not have enough data, because this bridge was built in 1935, we assumed that the connection at the abutment to beam connection is pinned, because there's no bearings. But in fact, when we look at the mode shapes, we could see that there's a sway mode, so the connection has to be changed. So we freed the longitudinal translation at the abutments, which actually gave us this mode shape, which is similar to what we saw mode shape in the FE model, which is similar to what we observed in with the modal analysis. So the second mode, which is pier and deck bending mode shape, was observed as here. So I could say that the dark blue line shows that one side of the mode shape, and the light blue line shows the other side of the mode shape. So observed at 18.75 Hertz, an initial FE model assumed, predicted it should be around 16.37 Hertz, but the mode shape is a bit different, as you can see here. And but when we made another update to the FE model, we found that by fixing the vertical translation of the pile base, we found that we could get we could improve the mode shape to match with what we noticed. And this updated FE model was used to simulate what would we see because of the Scour repair program. We noticed that because of the repair, we should notice about the sway mode should change up by 0.14 Hertz. The pier and deck bending mode should change by 0.5 Hertz. But the problem was that, if you could remember, the inherent variation is more than that. So inherent variation was about 0.6 Hertz for the first mode, 0.8 Hertz for the second mode. So because of that, when we look at the same data set, so 6 data sets before in blue color and 6 data sets after in red color, you can see that we can't really detect the change of natural frequency because the inherent variation is larger than the change due to the natural change due to the Scour. So in summary, ambient vibration was measured during the Scour repair program at Baildon Bridge. So we detected 2 mode shapes, and according to the 2 mode shapes, we were able to successfully update the model. And inability to obtain high enough frequency resolution indicates a potential challenge for monitoring Scour of small span bridges with vibration-based methods. Thank you.